Cool. In this video, we're going to do modern periodic table. So I really just want to give us a rundown of how the modern periodic table is put together, um, the details of what's going on in there, what I expect you to know out of this, and um, yeah, that kind of stuff. Okay. It's not too terrible. We're going to be visiting the periodic table a lot throughout the course, and um, one big part of this course is being able to mine secret information out of the periodic table. And so we're going to dive into that over the course of the course. That's saying course a lot. But you get the idea. All right, let's do this. All right, so this is what the modern periodic table looks like, or a modern periodic table. There's lots of different versions of this. This is just one. I think this is the one from our book. But yeah, most of them look the same like this. There are some distinctive features that all periodic tables have in common. There are rows, although we're going to change the names and call the rows periods. And there are columns, but we're going to call the columns groups. Okay, and we'll refer to groups quite a bit as we do this. The groups are also numbered. Okay, there are unfortunately two schools of thought on this. The one that we're looking at here uses the IUPAC, IUPAC suggested guidelines of numbering the columns, the groups across 1 through 18. It makes perfect logical sense. But I think it loses a little bit of information in doing it that way. Okay, and then there's an older system that's still in play that's used a lot, especially in the United States, that has A's and B's, where some of the groups are numbered 1A through 8A, and they use Roman numerals, and some other groups are numbered 1B through 8B. Okay, and we'll see both of these numbering systems. I want you to use the A and B number system for most of the time, which is not shown on this one, which was probably a bad choice, but yeah, so that we can keep those under control and know what we're talking about and always be talking about the same thing, because the A and B group numbers have a lot more information in them that is lost when you look at the 1 through 18 numbers. Another thing to point out is that there are the rows, the periods have numbers as well. 1, 2, 3, 4, 5, 6, 7, and they're not always shown there. You can just count them down. And we're going to see that this has significance. And a lot of times this number out here is called n, and this is a quantum number. And we will get into that kind of stuff a little bit later on when we start talking about a little bit more detail on how atoms and stuff are put together. Okay, so something about, excuse me, why the A and B group numbers are a little bit better. We can split the periodic table into smaller chunks, I guess, big chunks, but smaller than the whole thing. Representative elements, or called main group elements, these are the A groups, and they're on the outsides, the first 2 groups and the last 6 groups. Okay, these are the A groups, and these have mostly predictable properties. Okay, something else we'll get into, and this one is colored that way as well, is that metals and non-metals, and we'll get into what that means in a bit here, are colored differently on the periodic table as well. And we see that as a common theme as we go. But you'll notice here we have a mixture of the types of elements here. There's a representative sample of all possible kinds of things here. The B groups are in the middle. Okay, these are transition elements, or called transition metals, because all of the ones in the middle are metals. These are the B groups. Their properties are a little bit less predictable, but they still follow patterns. And we'll talk a lot about transition metals in Gen Chem 2. Okay, and we'll do some stuff with them in this course as well. Down below, okay, they've been kind of kicked out of the periodic table, are the lanthanides and the actinides. These are rare earth metals. These are technically B groups. These are not transition elements, and their removal from the bulk of the periodic table was a style choice years and years ago, and all of these elements actually fit. Well, all of these elements here actually fit in between here. So if you look as you go across, we have number 57, and then we have number 72, and that's because 58 through 71 have been pulled out down here. Okay, so really these 2 rows of 14 belong in here. And just as a way to make it fit nicer on pages and papers and posters, they've been pulled out. Okay, and for reference, lanthanides, these are called lanthanides because they're like lanthanum. They're period 6, and actinides because they're like actinium. These are period 7. Okay, this was a relatively big deal back in the when this was going on, right? When people were figuring stuff out. So we can't I can't talk about this without talking about Glenn Seaborg. Glenn Seaborg is amazing. Um, but Glenn Seaborg lived in the 20th century. He worked on transuranium elements. He won a lot of prizes and awards. He was involved in the Manhattan Project. He got a Nobel Prize in 1951. And for a while, he was the U.S. Atomic Energy Commission chairman. But so at the time, and now, I mean, it still holds true. Uranium is the largest naturally occurring element. Uranium. This is number 92. And so what they were doing, and part of the Manhattan Project was, building atomic weapons, but a lot of that involved uh, playing with atoms and doing atomic theory and that kind of stuff, trying to discover new things. And so part of their goal was synthesizing new elements, and the elements that they've synthesized are elements beyond uranium or transuranium elements, and we'll talk more about these in Gen Chem 2 as well. And so at the time, the lanthanides, which are all naturally occurring, were pulled out and put down here, right? This is period 6, and they all go right here between lanthanum and hafnium. Okay, were pulled out and put down there because they knew what was going on. Um, at the time, the last 3 elements, thorium, protactinium, and uranium, were figured to be transition metals because it just fit the pattern that they were used to. And it wasn't until Glenn Seaborg came along and said, look, I don't think these are transition metals. I think these are a new set of elements, and they are more closely related to actinium, and they're more like the lanthanides, and so we should call these actinides. And so there was kind of a debate in the 60s, and I imagine this got really heated at some point, saying that thorium, protactinium, and uranium really should be down here with cerium and them. And so Seaborg recommended that these elements be pulled out and put down underneath um, the lanthanides and called them actinides. And you know, people debate about this and do whatever, but eventually it was figured out that yes, Seaborg was right, and he had his hand in making a whole lot of these elements, and so they did that. But he was I guess the first person that had an element named after him while he was still alive. Right? There's a lot of elements named after people, but he was the first one named while he was still alive, and this happened while I was in college. So that's pretty great, I think, actually. Yeah, so that's my little spiel about Glenn Seaborg. Here he is showing off the edited pieces of the periodic table up here. All right. So let me get back to something more relevant. Let's talk metals and non-metals, right? The periodic table is full of information, right? There's layers and layers of stuff, not unlike onions. And so maybe we'll just say that onion is our secret word for this one, right? So we have these layers and layers of information. And one of those layers is whether things are metals or not, okay? So we kind of want to know what, and I always start with metals because it's easier for us to grasp because they have, when you say metal, you picture something particular in your head, right? They're lustrous, they're shiny, most of them are silvery. I bet you can think of two right off the top of your head that don't look silvery. They're conductors, both electrical conductors and thermal conductors, so electricity and heat. And they're both malleable and ductile, and these are probably terms that you may or may not be familiar with. Malleable has to do with, can you pound it out into thin sheets, right? Is it workable like this? Okay. Metals are malleable, so they can be pounded into thin sheets. That's why we have like aluminum foil or tin foil. We can get really thin gold leaf. Remember Rutherford's gold foil experiment, right? That's all because they're malleable. Ductile is making wires. So all the electricity running through everything is done with wires, okay? And the wires are possible because metals are ductile, okay? And so all of them, all the metals are on the left side of the periodic table. You'll notice there's this line that goes right here that I wish had a name, but I don't think it does, okay? That separates metals from non-metals. Okay, one thing I want us to point out is the line continues over here. Hydrogen is not a metal, okay? Even though it's on the left side of the periodic table. On the right side of the periodic table are non-metals, and I've kind of cropped this a little bit better to emphasize that hydrogen here is a non-metal. Non-metals are harder to describe generally because they're very different from each other, but they're everything that a metal is, a non-metal is not. So they're dull and they're very colorful, right? They're not super shiny, right? They're not malleable, they're not ductile, they're not conductive, okay? They're insulators, they are brittle, and they're colorful. So if you try to make like sulfur foil, you're not going to. You're going to get a chunk of messy powdered sulfur crap, which is not really what you want. So the non-metals are on the right side. Notice there's a lot fewer non-metals than there were metals when we look through this. Okay, in between, there's a gray area, or in this case, a purple area, called metalloids. Sometimes these are referred to as semi-metals. Okay. They are usually kind of shiny and silvery, but they're also brittle, okay? And they're often used in semiconductors and ceramics. There are a bunch of these, depending on what we get into. What I really want us to remember is that aluminum is actually a metal, not a metalloid. And everything else that touches that stair-step line we can consider to be a metalloid. Okay, boron, silicon, germanium, arsenic, antimony, tellurium, astatine. Although astatine we're not going to work with because it's super, super radioactive and doesn't live for very long. Yeah, our textbook qualifies polonium as a metalloid. So this should be purple as well. Okay. All right. Getting long here. All right. So metals on the left, non-metals on the right, metalloids, semi-metals in the middle, the stair-stepping line. Okay. One last thing we're going to get into, and that is, here's our summary. I should have put this up when I said the other stuff. Okay. This is why I use this picture from this other book, is because it has the extra bits around the edge to show us this stuff. Okay. Remembering that polonium is a metalloid, then we're pretty good. Although it's radioactive as well, so we're not going to stress about it. All right. So in addition to all of this, the representative elements, the main group elements, have been given names to the groups. Okay. And it's just a way to keep, I don't know, describe things. That's how people describe things going on. It's a hold back or from the early days. But every group has a name. Okay. Alkali metals, alkaline earth metals on the 1A, 2A, and then on the other side, we have icosagens, tetragens, pnictogens, yes, the P is silent, chalcogens, halogens, and noble gases. And yeah, I mean, okay, alkaline, there's some of these that are much more important than the other ones. And even icosagens, tetragens, and pnictogens have fallen out of use, and no one uses those anymore. I threw them in there as a historical moment, okay? But These 5 are still in use to today, and we're going to be using them and thinking about them a lot, especially when we start talking about the chemistry of these things. We can say, well, halogens do this and alkali metals do that, and we're going to do a lab about alkaline earth metals and all this stuff. Okay, so we need to know what those names are. So know these. All right, and in case you can't see them, this is 1A, 2A, 6A, 7A, and 8. Whoa, that's not the right letter. 8A. Okay. And then just for reference, okay, a chemist will always have a periodic table on hand. Okay. This is the periodic table you're going to get on the exam. Okay. It has both the A group numbers and the B group numbers. Okay. We'll dive more into what those mean and how they're weird, right? 1A, 2A, then it goes 3, 4, 5, 6, 7B, 8, 8, 8B, 1B, 2B. It's weird. Transition metals are weird. And then 3, 4, 5, 6, 7, 8A on that side. Okay, I'm keeping to the convention with the classroom periodic table where the blue ones are liquids at room temperature, the red ones are gases at room temperature, and the black ones are solids at room temperature, and the gray ones are synthetic. Okay. If you need anything, let me know, and I'll see you around.